Welcome everyone here at Netch Analyzing and Testing, live at the JEC World Composites Show 2017 in Paris. Actually, we're not in Paris, but what we will do now in this Meet the Expert format that we will repeat as at Netch Analyzing and Testing for the second time. We presented at the JEC World Show a short demonstration of the Netch DEA 288. And what Alexander Kalupka and I will do today is we will just repeat this short demonstration to show you what we did at JEC Show for the ones who missed it. So to start, what we will do in the next 10 minutes, we will show you how to fully cure a carbon fiber reinforced prepreg using the Netch DEA 288. You will see some applications, what you can learn about the material, about the curing behavior, as we will follow the entire curing process of a carbon fiber reinforced prepreg with the Netch DEA 288. And you will learn two things from that. The first one, you can learn how the Netch DEA can make your process, your carbon fiber processing safer, because you have a sensor that can follow the entire curing process where the curing is happening inside the mold. You will see that later, what Alexander will show you. And secondly, this gives you also the possibility to learn how this can make your process faster, because once you know the process and what is happening inside the mold, of course, this gives you the opportunity to manage your process better, decrease curing time, or, and in the end, of course, save costs.
Yeah, also welcome from my side. My name is Alexander Kalupka. I'm in the R&D team for the DEA 288. Dielectric analysis is the most sensitive technique to follow the curing behavior of a thermoset inside a mold. And the DEA 288 is the easiest way to follow this curing behavior inside a mold. Today, you will have a look at how we cure a SGL carbon fiber prepreg material inside a mold.
So I didn't introduce myself. My name is Tobias Pflock. I work for Netch Analyzing and Testing as a business field manager for polymers. So what Alexander already showed you, this is the sample that we will prepare today. It's kind of small. I don't know. You can go closer with the camera. Well, you don't see much because it's black from the carbon fibers. This is a UD carbon fiber reinforced prepreg. And so we will look at the curing. This is a thermosetting polymer as a matrix. So Alexander, I'm asking you, how can I, so well, I'm a part producer for composites, and one of the points is to judge the quality of my curing process. So what would you do, what could you think of to judge the quality of the curing of such a material?
Yeah, I would be interested in the rheological behavior of this material inside the mold.
Okay, that's a good point. The first thing, we could look at rheology. So we could put this inside a rheometer, and well, this is very commonly done, that people look at the development of the viscosity of such a resin, and you could see the start of the curing.
Yeah.
However, it is not so easy to look at the end of the cure. So it's, let's say, kind of hard to follow the entire curing process using a rheometer in a coupon size in the lab. And of course, it would be kind of hard to take a rheometer inside the mold where my process is actually happening.
Yes, of course.
Yeah. Okay, so can you think of another way to judge the quality of the curing?
Yeah, we can observe the heat enthalpy of this material during cure.
Okay, so I assume Alexander is knows what he's talking about, because you've done that many, many times. You can look at the curing enthalpy that comes from the exothermal reaction as the curing occurs and the cross-linking occurs inside my sample. Regularly, we would do that by DSC.
Yeah.
I guess that's also the method to look at exothermal enthalpy. And that is very commonly applied. A second parameter, you would also be able to see the glass transition temperature. So this is commonly observed in the DSC. However, you find out very high fiber contents, and it's getting harder and harder to see the curing itself. So the DSC is not as sensitive in the end to see the full cure. So other ideas, maybe something that is also applied in the industry?
Yeah, dynamic mechanical analysis.
Okay, dynamic mechanical analysis, short DMA. So we could use a DMA.
Yeah.
We also have an edge DMA, 242E Artemis, or the DMA Plexor that we could use. And that is very commonly applied, for example, in the aerospace industry. I know that every part that leaves aerospace production is qualified by measuring the glass transition temperature using DMA, dynamic mechanical analysis. And of course, that's also what we can do with our DMA. However, it's a very tedious thing to do because you have, for every sample that you prepare, you have to make a special sample. You cut this out, you take this out of your process, and you have to look at it in a separate measurement in the DMA. That takes you 1 hour, that takes you 2 hours. Then you know the glass transition temperature, and then you can give the part use the part for further processing. So that's a very tedious process. The question is if we can do better, and the answer is yes, we can do that using the NETCH DA288 because we can follow the entire curing process, including the post-curing, with very high sensitivity, and that's what Alexander is about to show us by preparing this coupon testing with today's experiment.
Okay, so we're ready to start. Let's have a short look to the equipment we use for today. This is our NETCH DA288 dielectric analyzer. Here you can see we have one sensor plugged in channel 1. We use this type of sensors here. It's a tool-mountable sensor. The big advantage of the sensor is that we are not only recording the dielectric signal, so the curing behavior of this material, we have also a thermocouple integrated inside, so we can also follow the exothermal heat of this material during cure. This sensor is integrated into the mold of this DEA lab press you can see here inside. So we're ready to start. I will show you how easy it is to use the NETCH Prototype software to start a dielectric measurement, and then we'll have a look at the curing behavior of this material. So you have just to put in a few things for sample preparation. Here we have to use our DEA lab press. We have to put on the DEA lab press as a hardware device, and we use the tool-mountable sensor with the integrated thermocouple inside.
Maybe, Alex, if I come in, I can also show you that here, this is TMS. This is where you decide in the software.
Yeah. As a temperature profile, we do an isothermal cure at 170 degrees Celsius for about 4 minutes to follow this curing behavior of this material. So now we are ready to start. I will start the measurement, then we will see how I put in the sample into the mold of the press, and we will follow the signal of this material. So now I'm using this carbon fiber prepack material. Open the door, put in the material into the mold, close the door, and we will have a look what is happening now. Okay,
we see that something is happening already. We have a look at this green signal here. Well, you see the green curve. This is nothing else but the dielectric signal. Also, we see a red curve here that is tracing the temperature as it occurs.
Yeah.
Yeah, Alex, just tell us what is happening with the DEA here.
Yeah.
What can the DEA show us?
What you can see here is a very sharp decrease in ion viscosity. This indicates that the sample has just arrived at the sensor surface. Then you can see a very sharp decrease that indicates that the material is getting lower viscous. So here you can see a minimum. This is the point where you've reached the lowest ion viscosity that correlates to the state of the lowest viscosity you know from rheology results. Now you can see that the ion viscosity is increasing and increasing. The slope of this increasing ion viscosity gives us information about the reactivity of this material. So the slope is directly correlating to the reactivity, so the speed of cure at each point we measure here.
Okay, so we can just follow the curing as it goes along, but Alex, I have some more questions to you because maybe this went a little bit quick for the viewers. That just you just have some black disk and put it in the machine, and that went really fast. So first question is, how did you prepare the sample? Because normally I would think this is just a one-layer prepack. So how did you?
Yeah, we used 24 layers of this unidirectional carbon fiber prepreg from SGL.
Okay, so that's quite a representative sample, I would say, for coupon testing, as you would do in the lab. Second question, relating to carbon fibers. This is a conductive material, and well, actually it's not easily possible to measure a dielectric signal to follow the curing of a carbon fiber parts. How did you do that?
Yes, for sure. You're totally right. We have to put in a separating material. So we used glass fiber woven fabric between dielectric. Yeah, you can see that also here. You can see a glass fiber woven fabric between the dielectric electrodes and the carbon fiber material here. So the resin can feed through and the carbon fiber don't.
Camera can zoom in a little bit. Yeah, you see this is quite convenient. You just put it onto the sample and that's how it goes along. Next question, we still have some time. If we have a look at the instrument here, maybe Alex. So, well, we're just using one channel here. For the coupon testing in the Netsch lab press, that's very fine. But my question would be, why would you need these 8 additional or 7 additional samples? What is the use of that?
Yeah, if you have a very big mold, you're not interested in a one-point measurement. So you want to get the information from every part of this material. So we can use up to 16 channels, simultaneous measurements inside the mold. So we can have 16 points where we can put in a sensor inside the mold and measure the curing behavior of this material and the temperature at this point.
So from that, where this could be used is, for example, you have a mold that is like 1 times 2 meter in space. So you could place one sensor at the sample arrival to detect when the sample is coming into the mold, when material, for example, an RTM tool.
Yes,
when the resin is arriving and
for
inside
example,
your tool.
A rooftop of a car.
Rooftop of a car, yes. And you can just place the sensor at the most critical points in your mold because the Netsch DEA allows to trace the curing process where the curing actually happens inside your mold. So let's go back. Oh, you saw measurement is just finished. What will happen next?
Yeah, you could see that the software automatically shifts to the Proteus analysis part. So here we can see the just recorded measurement. We only will have a look at the ion viscosity. So the green curve you can see here. As you could see, I started the measurement before I put in the sample into the mold. So what we will do now is we will shift the signal to the point where the measurement really starts, so where the sample got into contact with the sensor. This point of the very sharp increase is now our point in 0 time. Now we will have a look at the most interesting points of this measurement here. So the first very interesting point is the minimum in viscosity, because this is the point where processing is much easier than, for example, in a pre-cured state. So it's a very low viscous material at this point. And the second point we can evaluate is the point of inflection in ion viscosity. You can see it here as a peak in the derivative of the ion viscosity. So I will change the time unit to seconds. The point of inflection gives us the information about the reaching of the gel point of this material. So this point correlates very, very good to the gel point you know from rheology measurements as a crossover between storage and loss modulus of rheology measurements.
So there were 2 points that we analyzed right now. The third point, of course, of interest would be when is the part fully cured? And that is something that you could follow if you trace this curve more and more. Once you reach a horizontal state, then I would say you're in the cured state. So with that, you saw that was quite easy. We also presented you how easy it was to apply the software. So I think this is also a point that is important if you employ such a technique. You do not have to be a pro in dielectric analysis, but you have to be a pro in your processing. We take care of the software and of the analysis. We could learn that you get a sensor for the sample arrival. You get a sensor for part that correlates to the lowest viscosity. You get a sensor for the reactivity of the slope here. And you get a sensor for the inflection point. And still you can trace, or the gel point, and still you can trace the entire curve of the curing as it goes along inside your mold. So we wanted to show you 2 things. The first one was how this can make your process safer, because that is an issue, especially in aerospace, for example, because we can tell you what is happening inside your process all the time, as we have a curing sensor that is placed inside the mold. Secondly, this can help to make your process faster, because there's this management saying, if you can't measure it, you can't manage it. So you can measure it now. So, well, that also gives you the possibility to manage your curing processes better, because you have a sensor to follow the curing. And I think with that, we're about through with our short presentation. As we regularly do now with our, in this Meet the Experts format, well, Alexander is still here, so I would just ask some more questions. We prepared some of the questions beforehand that are just very generally touching dielectric analysis. And I would right away start with the first one. I think we would still have about, let's say, vital 10 minutes, 10, 15 minutes, depending on how many questions still come in. For you to know, if you have questions in the meantime, there's a chat function at the bottom of your screen. So just type in your chat, the questions that you have. Please be aware that, well, we will have our mission control in the back to kind of control which questions we can answer right now, but no problem, we can get back to your question and answer them later on. Start the first question. Alexander, we use an epoxy system here. What about polyurethanes? Can I also look at curing of polyurethanes with the DEA?
Yeah, for sure. You have dipoles in polyurethane systems. You have mobile charge carriers. So two effects we can measure with the dielectric analysis. So as well as this epoxy system we observed today, we can also measure polyurethane systems.
Okay, so you get a very nice signal and you can also do that. Question relating to that already. What about unpolar materials?
Yeah, regarding the answer for the polyurethane systems, we have two effects we measure. So we measure polarization and the mobility of charge carriers, of ions, of electrons. For unpolar materials, we don't have polarization effects, so we cannot measure this. But we can measure the mobility of charge carriers and ions that will decrease during the curing process of a material.
Yeah, and if the mobility is decreasing, we can see something in the DA, so we can also trace these processes. Very interesting question that takes us a little bit away from curing materials. What about thermoplastics? Can I also use the DEA to see, the NETCH DEA 288 to see phenomena in thermoplastic processing?
Yeah, thermoplastics are very interesting materials today in composite processing. Yeah. So in thermoplastics, the phase transitions are very interesting. So glass transition, melting, crystallization. We can measure all of these phase transitions using the DEA 288. Okay,
that's very good. So that makes it a very sensitive and very widely used, or it's possible to use this in a very, very wide range of different polymer materials to know about my processing. I look on my screen here where I have some more questions. Let's say I'm interested in well, we saw this is kind of the industrial version already. What is the minimum configuration to kind of, what is the starting package to start with a DEA if I want to investigate my processes?
Yeah, the smallest version of the DEA is a slim version with up to 2 channels for measurement. As the smallest package for starting dielectric measurements, you can use the slim version and you need a sensor for measurement, and that's all. The software package is included with the DEA.
Okay, so that's very good. So comprehensive software, so I think this is a good starting package, 2 channels, and then you just look at your processes and you can manage them better. Second thing, talking about processing. There's different ways of processing. We were looking at pre-preg processing. That is still the most widely used technique. However, we just came from JEC show. Everyone is talking about RTM processing, of getting faster processing. So can we also look at RTM?
Yeah, for sure. We can look at RTM processes. We can look at SMC processes. We have an example here for an RTM process. This was done with the polymer engineering of the University of Bayreuth. We used IDEX sensor inside the mold here that come off to the DEA 288, and we monitored the flow front and the curing behavior of this material.
And in this case, we used this is a demonstrator from the lab tool they had at the chair of polymer engineering in Bayreuth. We used this glass fiber layup to see the sensor. So you could see in between, this is dielectric IDEX sensors that we could also use. Another question. Just in 2 weeks, another show is coming up, and that is the European Coatings Show in Nuremberg. Can I also measure coatings?
Yeah, you can also measure coatings. We are able to measure very, very thin layers of materials. So we can also measure coatings with very thin layers.
Okay, so this is also, especially epoxy coatings, I think you could just see that if we measure epoxy coatings for pre-preg curing, the effect of the material would be just very similar to coating materials.
Of course, yeah.
And that is also already commonly applied in the coatings industry to know about the curing behavior of such coatings, also different coatings. One more, UV curing. Can I also do UV curing because everyone wants to get faster?
Yeah, the DA288 is a very fast dielectric analyzer, so we have a data acquisition rate smaller than 5 milliseconds. So we can also follow the curing behavior of ultraviolet materials. Okay, and just for you to know, you can also get a lab furnace that has a setup for UV lamp, so you can all get this in a full package for evaluation in your laboratory, for example. We also have an accessory for humidity. Okay, humidity is also possible, also with dielectric sensors that we commonly have. Yeah, you can observe the humidity influence on the sample response. Yeah. And humidity is a common application of humidity is a common curing mechanism. So especially for the thermoplastic materials we talked about a few minutes ago. Okay, so that gives you also the possibility to observe this kind of curing process along the entire curing process. Some more questions that we got from the audience. First one would be how to measure the curing rate of the curve. Yeah, as you could see, here's a question from Finland. If you have a look at the increase of the iron viscosity, the slope of this iron viscosity gives you direct information about the rate of cure, so the cure speed at this point you're interested in. Okay, so if you look at the first derivative, maybe for example, this is your curing rate. Secondly, concerning the frequency, you selected one frequency, but generally dielectric measurements are multi-frequency measurements. How can I know about the frequency? Yeah, the frequency response is following that way that the higher the frequency, the lower is the response we get from the sample. So, for example, here we can see a very good dielectric signal of the sample. But if we reach a horizontal line here at the end of the cure for this 10 kilohertz curve we used now, then we cannot follow the curing process anymore with this used frequency here. So then we can switch to smaller frequencies, for example, 100 hertz, 1 hertz, or for example, 100 millihertz, and then we can follow the post-curing process of this material. Okay, well, this was an epoxy, 10 kilohertz is an appropriate frequency, you would say. Okay, well, I look again at our screen here. We have some more material. One was answered already. What is the matrix material used here? That's an epoxy resin. Yeah. It's an SGL epoxy. Next question. What can the DEA tell us about the degree of cure of epoxies? Can it help to identify a suitable post-cure schedule? Can you say something about that? Yeah, it's the question goes in the same direction we had with the different frequencies now. So you can use one frequency to follow the curing process. So if we have a look at this frequency we used here, 10 kilohertz, and for example the DSC measurement of this material, we cannot follow the heat enthalpy of the DSC after 2 minutes at this temperature of 170 degrees. But DA can with the 10 kilohertz curve. But also, if we cannot see any change in the 10 kilohertz curve when, for example, we reached a curing state of perhaps 95%, we can use lower frequencies to follow the post-curing process. And then we can adjust the post-curing process to see when is the material really fully cured. Okay, so I can correlate the frequency response at different times to the state of cure. So I think I can say we can answer the question with yes. I can use the DA as it is the only technique that can just stay with the process all the time and
this kind of sensor gives you the possibility that no other technique actually offers. And especially, it's really hard, I think, to place a DSC inside the mold. So that's what you can do with the DEA.
Yeah, and like all thermophysical behavior, also the dielectric follows the time-temperature superposition principle.
Maybe we take one more question. I see that I asked my board here. We have some more questions. However, I would say, let's say take one more question. I already thank you now for the very good response. That gives us the possibility just to come back to you, and we would use your questions, of course, and answer them later on as we contact you directly. Let's take one last question now here. Very common material, is it possible to analyze also BMC material? And I talk about high-filled polyester resin bulk matrix. So this is one of the most commonly applied thermosetting materials in the world. What about these kind of processes?
Yeah, we can also follow the process of SMC and PMC materials. So as we had the question before, when DSC is not able to follow the curing behavior anymore, when the degree of filler is too high, dielectric is able to. So we can see the curing process also in SMC and PMC materials.
Okay, let's say just one more. Can you go a little bit higher? I cannot see there. No, other direction, please. Thank you very much. Sorry. One more question about the glass transition. Can you monitor the evolution of the glass transition during the measurement, or can the TG be detected with a temperature scan? So can you say something about the glass transition temperature?
Yeah, the TG can be detected during a temperature scan. And for example, in epoxy systems, if you do rheology measurements, so now I'm answering to the question, can you monitor the evolution of TG during measurement? When you have rheology measurements, for example, for an epoxy system, you can often see a steps or S shape at the end of the curing process. And if you have a look at the loss modulus, you get a peak in the loss modulus in rheology results. This gives you the information that the glass transition runs over the actual process temperature. And this we can also see in dielectric measurements inside a mold, so in process.
Okay, so I think with that, well, there was a lot of things to see already. Thank you very much for your contributions already. Thank you for using this Meet the Experts format. There's just one more announcement. We will have a DMA user seminar that is available on our homepage. If you want to take part, we will discuss the DEA much more thoroughly then. Alexander and I will also be there to answer your questions and to see how you can use this for your processing. Thank you very much for joining us here in that format of Meet the Expert. You will also have a possibility to give us your short feedback, how you like this format and what we could still improve. Yeah, thanks from my side.
Yeah, thank you also from my side. Enjoy the rest of the day.
Enjoy the rest of the day. This is Tobias Block for Nature Analyzing and Testing. Thank you very much and have a good day. Bye-bye.